Okay, now let's move on with our band theory, which we started in the last class. And in the last class, we looked at the most simple extended solid, the infinite hydrogen chain. Why is that the most simple form of extended solid? Well, we reduced the problem from 3 dimensions to 1 dimension, and we built our one-dimensional chain using the most simple atom which is out there. That's the hydrogen atom, which is only the 1s orbital to be considered. So we have seen that we can construct crystal orbitals from the 1s orbitals of the hydrogen atoms using the Bloch function, and we have tested the Bloch function and derived the band diagram for the one-dimensional infinite hydrogen chain. So in a band diagram, as we have seen, we plot the energy versus the wave vector k, which is a quantum number in the reciprocal space, and we have seen that the wave vector k can adopt values between 0 and pi over a, whereby a is nothing else but the unit cell parameter within the one-dimensional hydrogen chain. Okay, we have seen that the energy of the crystal orbitals increases as we go from 0 to pi over a in an S-shaped fashion. So initially the slope is small, then the slope increases, and the slope again becomes smaller. So halfway through this band diagram, the slope is the largest. So these orbitals here in this region, they're essentially non-bonding crystal orbitals. We have also seen what causes this behavior. This is because the energy difference between the crystal orbitals is the largest in the non-bonding region, with the smallest near 0 and pi over a, respectively. Okay, now let's build on these results. In the next step, let us consider bandwidth. Which depends on the orbital overlap, which depends on the lattice parameter A. So of course, we can bring our hydrogen atoms in our infinite chain either closer together or further apart. So that will determine to which degree the 1s orbitals overlap. So the more they overlap, the wider the band will become. And you see here the band diagram for the one-dimensional hydrogen chain for 3 different lattice parameters computed. So here A is equal to 3 angstroms, and you see that the band is very flat. Okay, so the energy difference between the most bonding orbital and the most interbonding crystal orbital is very small. Okay, so that's an analogy what we have seen from molecular orbitals. So weak orbital overlap leads to a small energy difference between a bonding and an interbonding molecular orbital, and that translates to band theory as well. Okay, now as we decrease the distance between the 1s orbital, our band becomes wider. That is because the energy difference between the most bonding and the most interbonding orbital increases. Okay, and as we even further reduce the lattice parameter to 1 angstrom, the band again becomes significantly wider. Okay, so the difference between the most bonding and the most interbonding crystal orbital, well, determines the the bandwidth. So the bandwidth is an important well, parameter, concept in band theory. Okay, so associated with the bandwidth, there is the concept of the density of states. So the density of states is nothing else but the number of energy levels, or the number of crystal orbitals in a particular energy interval delta E. And that density of states depends on the bandwidth and how steep that particular band is, and what is the exact slope at a particular position within the band. All right, so now you see here a typical band structure for the one-dimensional hydrogen chain, and you see that, well, the slope varies, and that now translates to a different density of states. Okay, so the density of crystal orbitals, or the density of states, is the largest where the band is the flattest, and the density of states is the smallest where the band is the steepest. Okay, as a consequence of that, wide bands tend to have low density of states, and narrow bands have to tend to have high density of states. Okay, so another important concept in band theory is the Fermi level. So the Fermi level is the equivalent of the highest occupied molecular orbital for molecules. So it represents the highest filled crystal orbital. Okay, so the highest occupied molecular orbital molecule is important because it represents the highest energy electrons in the molecule, which determines many properties of the respective molecule. And similarly, the Fermi level is important because it determines many properties of an extended solid. For instance, electrical conductivity, magnetic susceptibility, specific heat, and so forth. And we will look at some of these properties in more detail a little later on in this course. Okay, so in the one-dimensional hydrogen chain, for instance, our Fermi level would be halfway through the band. Okay, at the position k is equal to pi over 2a. So why is that? Well, that is because each 1s orbital can contain a maximum of 2 electrons, but a neutral hydrogen atom, of course, the 1s orbital contains only 1 electron. So as a consequence of that, our band is only half full. Okay, now 50% of the crystal orbitals, these ones here, are bonding, and 50% of the crystal orbitals, these ones here, are anti-bonding. So that means that we can fill all the electrons into the bonding crystal orbitals. Okay, and this non-bonding orbital here at k equal to pi over 2a would be our highest occupied crystal orbital, okay, which determines the Fermi level. Okay. All right. Now you all know that hydrogen does not make an extended solid of hydrogen atoms with equal distance. In this case, our hydrogen would actually be, well, metallic hydrogen. So the hydrogen atoms would act similarly than metal atoms, for instance, lithium atoms, sodium atoms, potassium atoms, and so forth. But we all know that hydrogen doesn't do that. Hydrogen makes discrete H2 molecules. So how can we explain this behavior using band theory? And to order in order to answer this question, we have to first learn a little bit about folding bands. Okay, so a band can be folded when the unit cell parameter increases. Okay, so for instance, we can define our unit cell to be, well, the distance between the hydrogen atoms within our hydrogen chain that would define a sensible repeating unit in our one-dimensional hydrogen chain. In fact, it would be the smallest repeating unit. But of course, we could also define larger repeating units. For instance, we could define a repeating unit as a repeating unit that contains 2 hydrogen atoms. Okay, and in this case, the unit cell parameter would double. It would double from 1A to 2A. Okay, so what would that mean for our band? Okay, so a band considers always crystal orbitals that are made from a base set of atomic orbitals. So when we define the unit cell to contain only 1 hydrogen atom, then our base set of orbitals would contain only 1 s orbital. Okay? If we double the unit cell parameter, then our base set of orbitals would contain 2 1s orbitals. Okay? So now as we go from 0 to the maximum k vector, when we have a unit cell that contains only 1 hydrogen atom, we would go from 0 to pi a. But if we double the unit cell parameter in the real space, okay, we cut the k space in half, okay, because the k space is in the reciprocal space, okay. In other words, our k vector could now run only from 0 to 1 over 2a, okay. So in the unfolded band, which we discussed thus far, that would be halfway through the band, okay. So now at this position, pi over 2a, we would find the exactly non-bonding crystal orbitals. Okay, that would be this one here. And that would be this one here. So in both of these, the bonding and the anti-bonding actions exactly cancel out. One is just shifted by 1 lattice parameter A relative to the other. All right. So now if we define the unit cell parameter to be 2a, therefore this position here will be, well, the maximum k value that there can be, leading the band now to fold back. Okay, so graphically this is depicted here. So here we have our original band running from 0 to pi a. Now if we double the unit cell, our band will fold and will actually look like that. Okay, so now our most interbonding orbital, which is this one here, will not be at the position pi over a anymore. It will be at the position 0. So that's a consequence of doubling the basis set of the wave function. Okay. Now we can see that our basis set of the wave function is this one here, containing 2 1s orbital, which have opposite algebraic sign. Okay. So now we just add these up to form a one-dimensional chain without changing the algebraic sign of the space set of the wave function. Okay, we can just actually translate one base set by a full lattice parameter. Okay, Whereas here at the position pi over 2a, we would now have basically alternate algebraic signs for the base set of the wave function. Okay? So this is our base set of the wave function for this orbital. So basically, in the next repeating unit, the algebraic sign of that base set would be changed. Okay? And in the next repeating unit, the algebraic sign of the base set would again be changed. You see that this now leads to a non-bonding crystal orbital. The bonding and the anti-bonding interactions cancel out. Okay, so here we have a bonding interaction, followed by an anti-bonding interaction, followed by a bonding interaction, followed by an anti-bonding interaction, and so forth. All right? So we have another crystal orbital at this position, which is also non-bonding. So in this case, okay, we define the base set of our crystal orbital to be two 1s orbitals having opposite algebraic sign, and we alternate the algebraic sign of that wave function. Okay, alternately. Okay, so therefore in the next repeating unit, this one here must become negative, and this one here must become positive. In the next repeating unit, this one here, which is negative, has to become positive again, and this one here, which is positive, has to become negative again. Okay, you see that this results also in a non-bonding orbital, where bonding and anti-bonding interactions cancel out. And when you compare the difference between these two orbitals, then you realize that this orbital is just shifted by half of a lattice parameter into the direction of the chain. All right. So therefore, in sum, we can say, well, in our folded band, okay, we go from completely non-bonding, from completely bonding to non-bonding molecular, crystal orbitals, as we go from 0 to pi over 2a, but then we go back from, then we go from non-bonding orbitals to completely anti-bonding orbitals as we go back from pi over 2a to 0, or we can also say that we can define at k equal to 0 the most anti-bonding case here, okay? And then as we start flipping the algebraic signs of the basis set over the wave function, we can go continuously to a less non-bonding situation until we have finally arrived at a completely non-bonding crystal orbital. Okay? So this is the concept of folding bands by increasing, in this case, doubling the unit cell parameter. All right. So now to understand this concept in the context of the fact that we have hydrogen molecules, H2, rather than hydrogen metal, we have to consider the effect of the Peierls distortion. You probably have heard this, the concept behind the Peierls distortion under a different name, the name Jahn-Teller effect. Both are actually the same phenomenon, just that we usually talk about the Jahn-Teller effect when we talk about molecules, while we talk about the Peierls distortion when we talk about extended solids. Okay, so let us briefly review the Jahn-Teller effect for the example of cyclobutadiene. So the Jahn-Teller effect says that a molecule likes to distort, lower its symmetry when they are partially occupied non-bonding molecular orbitals. Okay, So by the example of the cyclobutadiene, that means that in the non-distorted state of the cyclobutadiene, where you have a regular square, you have, well, two non-bonding orbitals. You see the two non-bonding orbitals here. So these four orbitals represent pz orbitals of the carbon atom that make the pi system. Okay, so they stand perpendicular to that square. Okay, so for these two, basically the positive lobes would point up and the negative lobes would point down. And for these two here, the positive lobes will point up and the negative lobes, the negative lobes point up and the positive lobes point downwards. Okay, and there are two non-bonding orbitals, this one and that one here. The difference between this one and that one is just that in the first one, these two orbitals have bonding interactions, and these two orbitals have bonding interactions, whereby the interbond interactions are here and here, while in the other one, the interbonding interactions are between these two and these two, and the bonding interactions are being between these two and these two, or in other words, this orbital here is just rotated 90 degrees based on this one. So now in the cyclobutadiene molecule, how many pi electrons do we have? Well, we have overall 4, because each pz orbital carries 1 electron. Okay, therefore in the undistorted form of the molecule, there would be 2 electrons in each non-bonding orbital. Okay, the other 2 would be in the bonding molecular orbital. All right, so now you can see that by distortion of this square, the system can lower the energy of its non-bonding electrons. Okay, and can do it in principle in 2 ways. Okay, it can distort so that these 2 carbon atoms come closer together and these 2 come further apart. Yeah, or it can distort the other way, so that these 2 carbon atoms come closer together and these 2 atoms are farther apart, and that would resemble this structure here. So both of these structures are, however, chemically identical, because one only needs to rotate this molecule by 90 degrees to arrive at that molecule. So these 2 cases are actually indistinguishable. Okay, now let's look at the energy of the electrons for these 2 cases, which are essentially the same cases. So when you look at this orbital here, which is created by distortion of that orbital here, you see that the interbonding interactions are enhanced because the atomic orbitals having opposite algebraic sign come closer together, and the atomic orbitals have the same algebraic sign are further apart. Okay, for this electron here, the opposite is the case. These 2 orbitals come closer together, which are bonding, and these 2 orbitals come closer together, which are bonding, and the interbonding interactions here and here are being weakened. Okay, so therefore, this orbital here is lower in energy with respect to the non-bonding case, and this orbital here is higher in energy with respect to the non-bonding case. So now I need to consider that the non-bonding orbitals are only partially occupied. In fact, there are only 2 electrons in them. Okay, now both of these electrons can go into the bonding molecular orbital here. Okay, leaving the now interbonding one empty. So overall, we have lowered the energy of our electrons. So the same is actually true for the opposite distortion into this direction. It's just that now this orbital here becomes the bonding one, and this orbital here becomes the interbonding one, but still we can take our 2 electrons in the non-bonding orbitals and just fill them into the now bonding orbital. Thereby we have stabilized the energy of our electrons. So for that reason, the cyclobutadiene does not make a square. It actually localizes its pi electrons to form a rectangle. Okay, now the same can actually also happen in an extended solid. Okay, so here we have our folded band. And now look at these 2 non-bonding orbitals. So what will their energy become as we start to distort our one-dimensional hydrogen chain, in the sense that we bring pairs of hydrogen atoms closer together, bringing other pairs at the same time further away. Okay, so if we bring this pair closer together, and this pair closer together, and this pair closer together, we'll increase the distance between these 2 and these 2. All right. So now what does that mean for the energy of these non-bonding crystal orbitals? Well, you can see that here we enhance the bonding interactions and weaken the interbonding interactions. So for that reason, that crystal orbital will go down in energy. And for this crystal orbital here, we will increase the interbonding interactions and will increase the interbonding interactions and decrease the bonding interaction. Therefore, this orbital will go up in energy. So now, what will happen to, well, these 2 orbitals? You see that for these 2 orbitals, we increase the bonding interactions here and here and here, but we weaken the bonding interactions here and here. So therefore, the energy of this crystal orbital here at k equal to 0 won't change. And the same is actually true for this orbital here. Yeah, we increase the interbonding interactions here, but we weaken them over there, increasing them here, weaken them over there. So again, no change. Okay, but as we go from k equal to 0 to k equal to pi over a half, well, the bonding orbitals here will become less in energy as we go from bonding to non-bonding, and here the interbonding interactions will be enhanced as we go from k equal to 0 to k equal to pi over a. And you see that as a result, we are creating actually a band gap. Yeah. So there are 2 crystal orbitals at pi over 2a, which are now different in energy. Okay. So the jump in energy as we go from the highest occupied molecular orbital or highest occupied crystal orbital to the lowest unoccupied crystal orbital. Because remember, the Fermi level is actually here. All right, so that now explains why our hydrogen prefers to be an H2 molecule rather than an extended solid. Okay, as we distort our one-dimensional hydrogen chain to form H2 molecules, shown here, we lower the energy of our occupied crystal orbitals. Okay, we increase the energy of our unoccupied interbonding crystal orbitals, but that doesn't matter because these crystal orbitals are being unoccupied. Okay? And as a result, the distortion actually creates a band gap. So previously, we had a continuous band which was half filled. So the Fermi level was halfway through the band in the undistorted chain. But now as we distort the chain to form H2 molecules, we create a band gap. Yeah? So that also explains why our H2 molecule is an electrical insulator. So whenever we have band gaps, then our substance is electrically insulating, or in the best case semiconducting. If there is no band gap and we have a partially filled band, then we have an electrical conductor. All right. Now let's further expand on that. In our previous examples, wait a moment, I think I have to change now to this, that you can also see. Can everybody see the new slide? Everybody can see the new slide?
Yep, yeah, I can see it.
Good. In the previous case, we considered, well, the one-dimensional hydrogen chain, and in the one-dimensional hydrogen chain, the band runs uphill. Okay, what does that mean? Well, it means that as we go from 0 to pi over a, well, our energy increases. Okay? So that is, however, not always the case. When we look at other orbitals, rather than 1s orbitals, the bands sometimes also run downhill. So for instance, that is the case when we line up p orbitals in a sigma fashion to form a one-dimensional chain. So you see this illustrated here. Now a p orbital represents the basis set of our wave function for our crystal orbitals. Okay, and now at k equal to 0, we just add up the wave functions, never changing the algebraic sign. So now, however, what does that mean for the bonding situation of the resulting crystal orbital? You see, if they're all just lined up and the algebraic sign never changes, then you only have interbonding interactions. So the interbonding interactions are being maximized. So this lobe here, which is positive, would overlap with this lobe here, which is negative. This lobe here, which is positive, would overlap with this lobe here, which is negative, and so forth. Okay? So that would mean that at k equal to 0, the energy would be maximized. You would find the crystal orbital with the highest energy. So now, what about the position k equal to pi over a? So in this case, the algebraic signs of the wave function would alternate. So in practice, this would mean that I would have to flip every other p orbital in the crystal orbital. Now you can see that this maximizes the bonding interaction. Okay, so this lobe now would overlap with this one, and you see they have the same algebraic sign, creating bonding interactions. This lobe overlaps with this one. You see that they have the same algebraic sign, leading to bonding interactions. This one overlaps with this one, creating bonding interactions, and so forth. So overall, this crystal orbital at pi over a would have the smallest energy. Okay, so now all the other crystal orbitals would be in between, and our band would effectively run downhill. And at k equal to pi over 2a, we would find, well, crystal orbitals with a non-bonding character, exactly non-bonding character. All right, now let us look at a more complex example of a one-dimensional chain which contains now multiple orbitals. For instance, we can think about a one-dimensional fluorine chain. So which orbitals would we need to consider here for our band structure? We would consider the valence orbitals of fluorine, which would be the 2s orbitals, as well as the 2p orbitals. Okay, so now we would like to construct a correct band diagram under the consideration of bandwidth resulting from the degree of orbital overlap and the correct, well, correct flow of the band, meaning the uphill flow or the downhill flow, respectively. Okay, so now you see here 4 different bands, and only one of the 4 band structures is the correct band structure. So these 4 bands consider the 2s and the 3 2p orbitals. Can you tell me which of the 4 is the correct one based off what you have learned thus far? So if you have an idea, please speak out.
Well, so from the case where we were just looking at s orbitals, the infinite hydrogen chain, the way that the band graph looked like it ran from left to right, the slope started to increase and then decrease. And all 3 p orbitals started with the band having higher energy on the left side and lower energy on the right side. So just from that line of thinking, I would assume option B to be the correct one.
Yeah, good thought and good explanation, and your thinking goes into the right direction, but there's one other aspect to be considered, which is that the p orbitals, they do not exclusively overlap in sigma fashion. So what you saw in the previous case is an overlap of the p orbitals in sigma fashion. However, because the p orbitals have different orientation, only one of the 3 p orbitals can overlap in a sigma fashion. The other 2 have to overlap in a pi fashion. And when they overlap in a pi fashion, then again the band runs uphill. All right. So now, in which of the 4 cases, does one p band run downhill and 2 of them run uphill? Okay, you see that they're actually 2. So certainly this would be wrong and this would be wrong. Yeah, but we would have still 2 cases to distinguish. This one here, C and D, they look very similar, but when you look closer, you can see that for the case C, the bandwidth is larger than for D. When you look at the band that is formed from the sigma overlap of the 2p orbitals. Okay, so now C is correct. That is because sigma orbital overlap is stronger than pi orbital overlap. that means that the sigma band must be wider than the pi band. Okay, so now I see here in the case D, the bandwidth for the pi orbitals is about the bandwidth for the sigma orbitals. Okay, which is not a good representation. A better representation is that the bandwidth for the sigma orbitals is larger than the bandwidth for the pi orbitals. All right, so that renders actually C to be the correct answer. Okay, there's one more aspect to consider here, which is that the band for the p orbitals that overlap in the sigma fashion and the band that forms from the 2s orbitals cannot cross as shown here. So when you actually consider the orbital overlap of the p orbitals alone, as shown here, separated from the orbital overlap of the 2s orbitals, you see that these two bands would cross. Okay, so now, however, you see that in the real band structure, this is not the case. They do not cross. So why is that? So this is because the bands from the 2pz orbital can mix with the band or interact with the band formed from the 2s orbital because of suitable symmetry. Okay, you know this actually also from molecular orbital actually from your first year probably, when you just have discussed the diatomic orbitals like N2, O2, and F2. Okay, you have learned that the 2s orbital and the 2pz orbital that make the sigma bond can also interact with each other because they have suitable symmetry to overlap to form molecular orbitals. Okay, and the same can also happen with bands. So the 2pz band can actually interact with the 2s band, and the interaction is the more strongly, or is the stronger, the closer the crystal orbitals become in energy. So that means that, for instance, this crystal orbital here and that crystal orbital over there, because of large energy gap, hardly interact with each other. Just like atomic orbitals with very different energies, they do not interact with each other. Okay, but as the energies become closer, the interaction increases, and that leads to the fact that the bands bend away from each other, avoiding this crossover. Okay, so bands that have suitable symmetry to interact with each other never cross. Okay, and in fact, due to the mixing of the bands, okay, they bend away from each other so that they do not cross. Okay, so this is another point that you have to keep in mind when you construct band structures. So you must avoid that bands that have suitable symmetry to interact with each other cross. Okay, so this is, for example, not the case for the pi bands here interacting with the sigma band. So because they stand orthogonal to each other, they cannot interact with each other. Their symmetry isn't suitable, and therefore these bands can cross, and in fact, in this example, they do cross. Okay, so thus far, we have only discussed hypothetical one-dimensional chains of atoms Now let's move over to one-dimensional extended solids that exist in the real world. So one example is a polymer, polyacetylene. Okay, so in polyacetylene, you have zigzag chains of carbon atoms, whereby each carbon atom is sp2 hybridized. Okay, and you have alternating double and single bonds respectively. Okay. So that polymer chain is a rigid chain which resembles a real one-dimensional extended solid. Okay, so now I have learned from organic chemistry that when you have alternate conjugate double bonds, that you can also write a resonance structure, okay, in which case, in this example, the double bonds would be located here and here and here, and the single bonds would take over the positions of the double bonds. And I've also learned that in the reality, you actually have a delocalization of the electrons. And that would resemble this structure here. So now this picture is actually a flawed picture. When you look at the real crystal structure of polyacetylene, then you can find that the pi bonds, the double bonds, are actually really localized. So you find alternating shorter and longer atomic distances, which argues that, well, our pi bands are actually localized. They are not completely delocalized over the entire polymer. All right. So now, can we explain that phenomenon also with band theory? And the answer is we can. We can say that, well, within our polymer, we have a pi system of pz orbitals, okay, which stand perpendicular to the paper plane. Okay, so we have a chain of pz orbitals. Okay, so now because of the zigzag nature of our polymer, our unit cell would actually contain 2 pz orbitals. Okay, so now what would be our band structure in the case that our pi orbitals would be, or pi electrons would be completely delocalized? Well, then our carbon-carbon bonds, bond length would be all equal. All right. And the electronic situation could be described by a band structure in which we have folding band, whereby this orbital here would be the most bonding crystal orbital, okay, at k equal to 0. And this orbital here would be equal to, that would be the most interbonding crystal orbital we can think of. Okay, and it would also be at k equal to 0, just because these two orbitals would be the basis set of our wave function, and you see that the algebraic sign has never been changed within the chain. All right, now when we start out from here, we can start flipping the algebraic sign of basis set of our wave function that would introduce nodes, and eventually we would go from a completely bonding situation to a non-bonding situation here, pi over 2a or pi over a prime, if we consider a prime to be equal to 2 times the diameter of 2 times the distance between two p orbitals. So further, we would understand that as we go from this orbital here at k equal to 0 to pi over 2a, our crystal orbitals would become more bonding until they also become completely non-bonding. So you see that this folded band looks very similar to the folded band in our one-dimensional hydrogen chain, in which we have doubled the unit cell parameter A. So now you need to consider where the Fermi level is. So each of the two p orbitals contains one electron, and therefore our band would actually be half filled. That means that all these crystal orbitals would be filled, and these crystal orbitals here would be empty. Okay, so now again, this is a situation in which a Peierls distortion can take place. We have a partially filled band, and whenever we have a partially filled band, that gives rise, that gives a potential for the Peierls distortion to happen. Okay, so as we bring well, as we localize the pi bonds, so the a band gap opens. Okay, so one of the two crystal orbitals, which are completely non-bonding in this case, becomes bonding, and the other one becomes interbonding. So we have overall stabilized our electrons because, well, our band is only half filled, and we can fill all the electrons into the bonding crystal orbitals. Okay, so that explains the localization of the pi electrons. It also explains why our polyacetylene is not a conducting material. So in this case, it should actually be an electronically conducting metallic material, but actually we have an electrical insulator in the real case, and that is because of this band gap. All right, so I see we are at the end of our time. In the next class, I will discuss another example, Krugman's salt, which is a fascinating compound, but let's stop at this point.